I would like to present the program DC-Pilegroup. You see here are two program groups, DC Soil and DC Foundation, and the Pilegroup program is one of the group DC Foundation. So this program comes with two options, two versions of the program. There is a small program version, DC-Pilegroup Lite, which supports the analysis of pile groups where the slab is only used for transfer of the loads to the pile. This means that the load transfer to the soil is done only over the piles. And second program version, DC-Pilegroup Pro, is intended for pile groups and combined pile-raft foundations. That means that under the slab we have an elastic bedding. We have loads transferred by the slab and by piles, and we have the mutual influences from the slab bedding to the piles and from piles to other piles. And this method for combined pile-raft foundations, there is quite a number of different analysis methods to be used. For example, in the book Recommendations on Piling, there are tables for the effect of the piles, but these are not very suitable to be used in software. So what we use is a method described by Elgendi, Harnisch, and Kani. This paper here, it was published in the German Bautechnik in 2006. And this method uses the effect of mutual influence between slab and piles and between piles and piles by calculating a larger deformation, a larger settlement of the piles due to this mutual effect. So this can be seen in the configuration. If we go to settings configuration here, you see that these mutual effects can be switched off or can be used if you have the large program version DC-Pilegroup Pro. Effect from slab to piles and the effect from piles to piles. As well, here in the configuration, we have some important parameters concerning the speed of the analysis and the effect of convergence. It's a quite large iteration, how the loads are transferred from the slab to the piles. And if there is no convergence, you might change this factor. This describes that the pile forces from one step of the iteration are used from the last step and partly from the step before the last step. So you can give a percentage here to use, for example, 80% from the last step and 20% from the step before. And you can change this value between 0.5 and 1 so you might have a better convergence of a special iteration. And concerning speed of the analysis, this is a matter of how exact this convergence must be. So if you have very large pile forces, for example, 1,000, 2,000 kilonewtons, you will not able to calculate to a very exact pile force of only a difference of 5 kilonewtons, for example. So for high pile forces, you might define a higher difference between two iteration steps, for example, 50 kilonewtons. And in this case, convergence is much faster and the analysis time is much shorter. If we look to the basic parameters here, we have first the definition of the analysis standard that you already saw in DC-Pile. For example, Eurocode 7 comes with predefined national annexes for Germany, Austria, France, Great Britain, Italy, and Spain. And it is possible to define free analysis standards for other countries, for example. And all these parameters are predefined. It's the same that you have seen in DC-Pile already. Here, basically, we have two methods of calculation. If we have the Pro version of the program, the standard analysis method is the verification of any pile load. So for any single pile, the load must be smaller than the maximum design value of the resistance from skin friction and end bearing. But especially for combined pile and raft foundations, we have a second method to calculate, which is called the method with pile failure, which means that the piles might punch into the soil. They have their maximum characteristic resistance, maximum characteristic load for the pile resistance. And if the piles are punching into the soil, there will be more load going to the elastic bedding under the slab. So with a larger deformation, we can transfer more load from the complete construction into the ground. For the slab, we can use the subgrade reaction method or the stiffness modulus method. And one point, again, concerning the speed of the analysis, we have a standard element size for the finite elements of the slab. And if you have a very large construction, 20, 30, 40 meters, you might use larger elements, so you have less analysis time for the calculation. And we don't need any more a refinement factor for the element size. In former times, it was better to use smaller elements near the support, near the piles. But this is rounded automatically, so we don't need a different factor than 1 for the refinement anymore. You can leave this with a value of 1, and this makes analysis much faster than if you use very many small elements. Now for the soil layers, the same as you have seen in DC-Pile, we need two groups of parameters. One is skin friction and end bearing for the longitudinal loading, for vertical forces in vertical piles, for example, or the load transfer in vertical direction. And you need the parameters for the calculation of the earth pressure, or the limitation of the horizontal bedding for horizontal loads, and transversal loading of the piles. You can define different soil layers here. For example, some gravel, which can be selected from the parameter suggestion here, down to a depth of 5 meters, for example, and a new soil layer, which should be some sand, down to 10 meters. And we can select the suggestions for skin friction and end bearing, the same as in DC-Pile. And you have the parameters for the passive earth pressure. So here we have the global soil layers with the depth over the complete area. And then it is possible, I need to put Poisson ratio here. And we have the option to define different bore points. For example, you might have borings at 4 positions here. I define the 4 bore points. I stop this input function with the right mouse button. You see that the button here is switched off. And then with double click, I can change these bore points. And I cannot change the soil parameters because these must be the same over all the area to have the option to interpolate between different points. But we can change the depth of the soil layers. So for example, 3.5 meters here and 6 meters and 50 here and so on. And the thickness of the soil layers are then interpolated at any point for the analysis. Now for the slab, we have different options. We can have a rectangular slab. We can have a polygon of an arbitrary shape, and we may have circular slabs. And for example, we define a polygon. You see that the coordinates are moving here in this little window. And we might define an L shape, for example, for this slab. And giving a certain thickness of the slab. The modulus of foundation can be defined here as a fixed value for the elastic bedding, or it might be calculated from the soil layers, which is some combined method between modulus of foundation and automatic modulus calculated from the soil layers. Now for defining the piles, we may enter single piles, a grid of piles, or a pile ring, for example, around a circular slab. And if we define a grid here along this line and with this width, we might define, for example, 8 piles along the baseline and 4 piles in cross direction. And then we can define the parameters of the piles. We must use one type of pile, but the parameters can change. So we might define 4 piles, micro piles, driven piles, and so on. And for bore piles, there might be, for example, different diameters and different lengths, but only one type of pile. So we have this pile grid, and the same in this area. Could have 4 times 4 piles. And then any single pile may be changed. So I could go here, double click this pile, and I can define an inclination in X and in Y direction, or the total inclination, for example, 30 degrees, in an orientation of 45 degrees to the horizontal. And then this pile is inclined here, different to the other piles. And what is calculated automatically if you have the grid entered before is a reduction factor for the elastic bedding for the horizontal load of the piles. So if a pile is a pile at the edge of a grid, it may have more elastic bedding, more support, or more resistance than a pile in the center of a grid. So depending on the load direction, to plus and minus X direction or plus and minus Y direction, the program tries to define the correct reduction factors, and this is used for the horizontal loads. Finally, for the loads, we can have concentrated loads, distributed line loads, rectangular loads, polygonal loads, and circular loads. And for example, there should be a wall here, so we have a linear load with a load case permanent, a dead load with a vertical value of 50 kilonewtons per meter. And we might have a polygonal load here over the complete slab in this L shape. So this is load over the complete slab with a load case Q, for example, a live load plus 10 kilonewton per square meter. So we have the load here over the complete slab area. And we can see all this in a 3D display. If I save this example, and we see that one pile is inclined here, we defined the 30 degrees in this 45 degrees direction, and all the other piles are vertical. And we see the different loads here, which are acting on the slab. Then for the results, we may define sections, for example, here through the slab. This should be a section A to show the section forces along this line. Now we have this example finished. I will not start the analysis here with this example, but I will open a predefined example because calculation will take quite some time, quite some minutes. So let's use an sample 2 here, which is already calculated. It's a little similar with some more load cases. And what is special for DC-Pilegroup is that it automatically creates all the load case combinations, like in DC footing, but unlike the other programs, here the load case combinations are done automatically by the program. So if we look into the results here, the full view, we have first the output of the input values for the soil layers, for the slab, for the vertices of the footing or the slab, the types of the piles with their parameters, the material of the piles, and the loads, and all the safety factors. And then we see here the table of the load case combinations. So, for example, permanent loads are applied with a factor of 1 without safety factor or with safety factor. The live loads are with safety factor or not acting at all. And we have the combination of the psi factors. So if one load case is the leading one and the other is not leading, it is multiplied with the psi factors. Then we see the maximum pile reinforcement for any pile. The punching design, which can only be done if the punching cone is not intersecting between two piles. And then we have the design of the bending reinforcement and shear reinforcement over the pile depth for all the piles. You see the maximum reinforcement is here at the head of the pile and a little less reinforcement here in a greater depth. And this is shown for all the number of piles here. And then we have the reinforcement in color areas. So you see the reinforcement in X direction at the bottom of the slab, Y direction, and the reinforcement at the top. And then the reinforcement along this section line that they defined. Now all the different load case combinations are following. I will go down to the end of the output, which is quite long, because the last combination mostly has the full load of all the loads combined, and I go backward through the last load case combination here. So we see along the section line the soil pressure, the deformation in different directions, the normal forces, shear forces, bending moment. We have, again, in color areas, the soil pressure, the deformation. Here, the maximum deformation is here in the center of the slab. Normal forces, shear forces, and bending moments. And then we see the section forces for all the piles with elastic bedding, bending moment, normal force, shear force, horizontal deformation, and soil pressure. Again, for all the piles here. And finally, we have the settlement of the piles. And here you see this mutual effect of the combined pile-raft foundation. We have a settlement from the pile load itself, and we have additional settlements from other piles and from the slab to the piles, to a total settlement here, which is much larger than the one from the pile load only. Then we have the verifications of the longitudinal and lateral load of the piles with comparison with the design value of the resistance. And we have the pile group factor alpha, which means that 63% of the load is transferred to the piles, and the other 37% are taken from the elastic bedding under the slab. Finally, the characteristic normal forces, the spring constants, as the piles are acting as an elastic support for the slab. We have the maximum and minimum utilization of the piles forces, and here the design values of the pile forces and the loads which are applied in this load case combination.